Okay, Robert, can you pick me up on this too? Okay. Well, since y'all late, my job is to try to put you all to sleep. So we're going to go over the NanoVNA. A lot of people have these, a lot of people don't necessarily use them. And we'll kind of go over how you set this up and how you use it. They're a little more complicated than some of the others because they have a lot more capability. So just to start with, like, what is a network analyzer to start with? Well, all of these, they generate a signal and they send out to a network. And they get a signal back from the network and they can determine characteristics of the network. So it used to be, not too long ago, scalar network analyzers were pretty common because they were cheaper and simpler. So with the scalar analyzer, it only measures magnitude. So it sends out a signal, gets a signal back. So that's like an example. My house is 5 miles from here. You don't really know where it is, but you know it's 5 miles. If you plug a voltmeter into a wall and read 120 volts, that's a scalar measurement. But for RF, they were pretty handy because you could calculate SWR, return loss, gain of a filter or an amplifier. But vector analyzers have more capability and they've gotten cheaper and a lot easier to use. So those have been predominant now. So an example of that, my house is 5 miles northeast of here, or some bearing, so you have a magnitude and you know what direction. So these things, that's what they measure. They measure what's coming back from the network. And you don't have to understand it, but that lets you calculate the complex impedance. I know Dave knows all about this stuff. But it basically is a real and imaginary number that comes back. Okay, from there it's all math. So when you look at the R, if you have an analyzer and it says R equals 40 ohms, X equals 30, that's all calculated from that real and imaginary number. SWR, return loss, Smith charts, those all use exactly the same data, okay? It's just different ways of looking at it. So there's also a couple different types of these things. So this is a rig expert, an AA230. The MFJ259 was real popular. This is the rig expert. Those are called one-port analyzers. You can see there's one port on the top. So they send a signal out of this port and it comes back on the same port. Okay, so you can still, measure SWR and all the stuff these do. But the incident is the wave coming out and reflected. They're both on that single port, and that's called an S11 measurement. Okay, that's a scattering parameter is the S, which again, you don't really know what that is, but the 11, the first digit is the receiving port, and the second digit is the transmitting port. So an S11 measurement means you sent it out on port 1 and it came back on port 1. Okay, the NanoVNA is a 2-port analyzer that has 2 connectors there. Yeah, like that, and like this. So it's similar. It sends a signal out on one port, and it can measure it coming back on the same port, just like all these others, or it can measure it on a different port. Okay, and the advantage of that is that's called a through measurement. So instead of just going and reflecting back like from an antenna, it can go through like a filter or an amplifier and back in. And when you do that, you can measure like the gain or the loss of a filter, a gain of a preamp. You can text duplexers, determine the gain, the bandwidth, and all of that. And that's called an S21 measurement because the output is port 1, the input is port 2. Okay, you can't do those measurements with a 1-port VNA. You have to have a 2-port VNA to do that. So this is going to run pretty long, so I'm going to kind of skip through some of this. So these are the 3 we just mentioned, none of which are actually in production anymore. This is turned into what's called a deep VNA now. But the MFJ and the AA Zoom have the same frequency range up to 230 megahertz. These go to 1.5 gigahertz. The MFJ has no graphing. It just had that 16 by 2 character display and a couple analog meters. So you really couldn't do a sweep measurement where you actually want to sweep across a frequency and look at that. The rig expert guys, there's a whole family of these too. They could do a single parameter plot and they have one marker, and we'll talk about what you can do with these markers later. And it's a pretty good 320 by 240 resolution. This guy, you can do 4 parameter plots at the same time. So this, you can do a Smith chart and you can do an SWR, but you can't see them at the same time. This one, you can see them at the same time and they're overlaid on each other. And it can have up to 4 markers. And again, we'll see where that kind of comes into play. And it's an 800 by 480 touch screen, so it has 4 times the resolution of the other one. You know, the MFJ and the Zoom things have either N or UHF connectors are pretty sturdy for outside. One of the knocks on this is these little SMA connectors. They are pretty fragile. And what you really do with these is they almost all come with like a 6 to 8 inch little jumper. It's a SMA male to male. And then you buy adapters, like this is a SMA to UHF, so you can plug your coax in there. Of course, the main part of it is it gives you a mechanical strain relief, so you don't put RG213 on here and break the connector off. And these also have a built-in lithium-ion battery, so when it does run low, you just plug it into a USB port and recharge it. The MFJ seemed like it had a lot of fiddling around to do kind of simple tasks. The Rig Expert's pretty straightforward. You say SWR and it plots an SWR plot. This one does a lot more stuff, so there's more options, and I'm hoping that this doesn't discourage you, because we're going to go through all the menus, and there's a lot of them. But once you go through it a couple of times, it's actually pretty straightforward how you have set it up to use it. The other thing is, even though it's much more capable, it's about 1/3 the cost of the other guys, so it's very cost effective. They were about $100, now they're about $130 with tariffs. Why I put this up there is I got an email once, and the guy said, well, I got this thing, which side do I hook the transmitter to and which side do I hook the antenna to? And I was kind of, at first I was like, what? I think he was thinking of these. These guys, you hook the transmitter to one side where it says TX, the antenna to the other. That's not a VNA, and the power does go through this thing, but you never drive power into one of these, or it's an X-VNA very quickly. So I really didn't even think of that till I got an email. So this is kind of a mid-range, kind of lab quality VNA. And so to be honest, when I bought this, I thought it'd be a toy. For $100, I mean, this thing's $25,000, and this is a mid-range thing. I mean, they go way up over 6 figures. So it's a 2-port, just like this. It's 3 gigahertz instead of 1.5. But I mean, it's a lot fancier. It's a lot more accurate and all that. So instead of using this for 15 minutes and putting it in the drawer as a toy, this isn't anywhere near as accurate as that, but it probably has about 80% of the functionality, and especially for what hams use it for, it's plenty good enough. So it's just amazing what you can get for around $100 anymore. So, and specifically, the NanoVNA, there's a lot of different types. The VNA-F and the H are 2 of the main kinds. So we talked about it before. You could do 4 simultaneous traces. You can do 4 markers. You can search those markers for min and max value. So if you have an SWR plot, it's easy enough to just move the marker over, but you can say find the minimum, and it'll find that and tell you what frequency it's on. You can control these things. There's programs. One of the main ones is NanoVNA Saver. Okay, what that allows you to do is you can actually hook a USB cable from here to your computer, and you can control this from your computer. You can set up the frequency sweep. You can set up how many points you want it to sweep. You could do all this stuff just from the computer. So that gives you a much bigger screen than playing with this little touch screen. One thing I'll tell you though, if you do it, all these grounds are hooked together, so when you hook a USB cable, you kind of hook a tail to this thing. And it will affect the RF measurements because you got that ground. So either get a USB cable that has ferrite built into it, or clamp one, or wrap it through a toroid or something, or a ferrite core near that cable to kind of isolate that from the ground system. Okay, another big thing you can save these readings is touchstone files. So if you make a measurement of your antenna, like an SWR chart or whatever you want to do, touchstone files, they're designated, they're .S1P and .S2P. The .S, it's a scattering parameter. 1P is 1 port, 2P is 2 port. Those are just text files. And so if you look at one of those files, it has the frequency of the measurement, it has the real part and the imaginary part. Okay, for a 1-port measurement, it just has S11. For a 2-port, it has S11 and S21. Those values can be read into programs like NanoVNA. So besides controlling it from that program, you take this outside, you measure your antenna, and then you'd like to do more work on that, look at it closer, different things, then you can bring this in. This one, depending, there's different ones, but you hold certain buttons or knobs and turn it on, this becomes a USB drive. So it looks just like a flash drive plugged into here. If you plug this into your computer, a disk will show up, and that's where those touchstone files are stored. So you just take those and drag them over to your computer. You can open those like with NanoVNA Saver, and you can see all of that stuff on your computer now to do different work with it and look at it more. SimNet, that used to be SimSmith. If you ever want to play with Smith charts, that is an unbelievably good program to learn with. But the kind of cool thing about that is if you want to simulate, you can actually have a 50 ohm source, like your transmitter. You can have coax, you can have matching networks, and you can have an antenna, and you can kind of model that. The thing that's neat about it is if you actually measure your real antenna, SimNet will actually move that in, and you can try different types of coax, different links, matching networks and all that, and it'll tell you like how much power is being delivered to the load, how much is reflected. It's really powerful to be able to take those readings that you take with this and move them into the other programs. So once you set all this stuff up to, if we're going to go through, you can save up to 7 different configurations on here. So say you're testing a 20-meter dipole, and you set it up and you calibrate it and do all this stuff, you can save that. So if you want to go back to that, you just simply call that back up, and all those settings will be there. You don't have to go through this every single time. These are my own personal opinions. Deep Elect, which is who makes this, Leon, BH5HNU, did several versions of this. So the NanoVNA is an open source. The schematics were out there, the beginning of the code was out there, so anybody could make one. So some of them are really bad. This one, he seems that where things need to be shielded, they are. It's a well-done design, and like I said, this is about 100 to 130 depending on the tariff situation at the time. If you find one on Amazon for $73, that may be okay, but it may not be. I mean, you're kind of taking your choice. This is well done, so I would just recommend buying that. One thing I will say, because I forgot to say at the beginning, if you want any copies of this, especially when you get into where we go through all these menus, I've got a PDF of this, so if anybody wants it, you can email me and I could send a PDF, and that'll have all the steps you can go through to do it. You also want to get some port savers. All those are is on these. This is a little male-female SMA to SMA male to SMA female. There's only so many insertions with these little connectors before they start wearing out. I mean, they don't have a lot of surface area. So basically, you just screw those onto here, and then all the putting on and taking off of these cables is done on this adapter. So if this thing wears out or you bend something, you can just take this off and throw it away and put it back on. The actual SMA connector that's soldered to the circuit board doesn't get touched. And that's where some people will break those, especially if they put a big cable on there and crack that. And then you need, like I said, these adapters from SMA to UHF, BMC, N, whatever you kind of want. And again, these are just my comments. And I get the metal enclosure. Most of these you can get either with a plastic enclosure or metal. This one's metal, costs $20 or $30 more, but the SMA connectors are actually bolted to that. So that relieves a lot of the stress on the SMA on the circuit board, and it's better shielding because it's all metal. So those are just kind of my personal choices. So great, so what can you do with this? Okay, this is a fan dipole I built like 100 years ago or something. But it's good to illustrate things. So we're just going to take this first one and kind of go down this and show you what this thing displays when it's got a trace up there. So the very top left is kind of self-explanatory. It's a battery. So it'll tell you the state of charge. It goes green, yellow, or red. And this thing, the charge lasts a really long time on this. The disk use, when we talk about the touchstone files going into this disk, when this acts as a USB disk, it's a 16 megabyte, okay, not 16 gigabyte, 16 megabyte, but touchstone files are just a few kilobytes. You can store hundreds of touchstone files on there. So if you're saying I use 10.8% of that space so far. Now the bigger one is the C4 and all that other stuff. So that's saying configuration 4. That's out of those 7 configurations. So the capital C means that it's been calibrated, and we'll go through this. And what you do is you set up a frequency range. You can see at the bottom it starts and goes from 13 to 23. And you run through the calibration, and that DRS-TX jazz, I can't remember what they stand for, it's like directional and reflected and something. That means you went through a whole calibration procedure, and that's capital C, uppercase C says you're taking these traces on something that's been calibrated for that exact thing. If I said, well, I want to go to 24 megahertz now, I could change that stop frequency, but those frequencies where it actually sampled to do the correction is close, but it's not on there anymore, and now we'll go to a lowercase c, saying you calibrated it, but you changed something, just to let you know. The port 1 power, that plus 1 dBm, he has 4 settings of how much power this will put out. -10, -4, -1, and plus 1 dBm. That's kind of a set it and forget it thing. You really don't have to go through that every time. For antenna stuff, I usually set it to the highest power, just figuring that'll be less noise that can get in there when I'm actually testing the antenna. So I generally never change that. The bandwidth in hertz, again, he's got 5 options there, 10, 30, I think, 100, 333, and 1,000 hertz. That just determines on how accurate this is in the smaller bins. You don't need that. 1,000 hertz is good enough, and that's the fastest sweep. As you make that bandwidth smaller, it takes longer and longer to sweep across. Okay, so again, that's kind of a set it and forget it. The VF is velocity factor. That only comes into play if you're measuring like length of coax, if you want to know how long your transmission line is or something. Again, it doesn't apply to anything else like this. And again, that's not just the NanoVNA, that's this or anything else. You need to know the velocity factor, which is how fast the wave goes down the transmission line. In the 301P, some of the older ones only did 100 sample points. This one, he has 50, 200, and 300, 301, because he counts both ends. Again, to get the best accuracy, you want the most samples. So that's another, you set it and kind of forget it and never mess with it again. Like we talked at the bottom, this is sweeping from 13 to 23 megahertz. On the right is the SWR scale from 1 to 10. So that's kind of a cute picture, but it doesn't really tell you much, right? I mean, you can see if 13 megahertz is the one on the left, that first vertical line is 14, so you're a little over 14 megahertz, and the SWR is pretty good. You can kind of guess over here, that's about 21 megahertz. But that really isn't very useful, and that's where the markers come into play. So you turn on a marker, so now all of a sudden you see more stuff. S11 says it's a 1-port measurement. That SWR1/ means it's 1 per division. So that's why it goes 1, 2, 3, 4, 5. If you wanted more accuracy on that, you can set that the SWR like to 0.5 per division, and that would say 1, 1.5, 2, 2.5. He generally defaults these things that make sense, so very rarely do I ever have to mess with that. And then the reading is the SWR, it's about 1.1. And you can see the markers at 14.33333 out of 3 is megahertz. So where that comes from is, if you think about this, I'm scanning over 10 megahertz, and I've got 300 sample points. If you divide 10 megahertz by 300, you get 33.333 kilohertz. So every sample point is going to jump by 33 kilohertz as he's going through here doing these samples. Well, so that's giving you a lot more information. That's pretty nice. But say I also want to know, what's the SWR up there on 15 meters. So I can move that marker over, which is fine. But say I want to see both of them at the same time. Okay. Well, then you can just turn on an additional marker. So now we've got 2 markers, and again, none of the others allow you to do this. And I can set that one at 15 meters, and I can see, 26.07 megahertz. I've got an SWR about 1.2. Now, one thing I like about this compared to like the rig expert can get this picture, can't do the 2 markers. When you hit do it takes about 30 seconds to scan through, and it'll draw this picture, then stop. This thing is constantly scanning, and it's about 1 second, about 1.5 seconds of scan. So this is constantly sweeping through those frequencies. So if you ever mess with dual band anything, some kind of law of the universe is if you make one better, it makes the other one worse. So if this was like 3 to 1 and 2 to 1, and you have somebody helping you, you can be looking at that and say, well, the one that's 3 to 1 SWR, trim this or lower it or do something. And while that's being done, you can see what happens to the other one. So as you decrease that, the other one may go up. But this is pretty much real time. You're seeing the sweep as it's being done. So that's real handy. I mean, there may be a particular special case, but it's nice you can see what's going on as you're doing it. Okay, well, what else can you do with two markers? Well, I might say, well, on that 20-meter band, how wide is it where I want under 2-to-1 SWR? So I set the marker 1 as close as I could get to 2-to-1 on the low side, marker 2 as close as I could get to 2-to-1 on the other side, and you can see from 13.9 to 14.7 megahertz, this thing's under 2-to-1 SWR. So you know what kind of thing you're dealing with there. The delta thing is just telling you the difference between those two markers. So that's like an 800 kilohertz bandwidth that it has between those two markers. We also said you can get more than one plot on there. So here's where they rolls their eyes. Okay, so that's an SWR plot, and of course the purplish pink is a Smith chart. So again, this is exactly the same data. That Smith chart is showing you exactly what that SWR chart is showing. It's actually giving you even more data because the Smith chart tells you what the resistance and the reactance is at every frequency. So as you move that marker around on the green one, say if you drag that on the green SWR trace, it'll also move that on that purplish trace. And each one of those will tell you what's going on. And if you look up there at the top where it says S11 Smith, again, if you have an analyzer and you look at that, it would say R equals 46.6. X equals negative 2.7 ohms. So that's what you're going to read on the logic analyzer that has like the R and X displays. With the Smith chart, you get all those read out directly. But again, this is all calculated from the same exact data, those real and imaginary numbers. Those two are equivalent. So we talked about this NanoVNA saver. So if you take that same data and read it into that program, some of these might look familiar. That one on the top left is the SWR we just looked at. Top right is the Smith chart we just looked at. The bottom left is the return loss, and the bottom right is the R and X values of that component. So this makes it look a little more like that $25,000 one now. You know, this you've got 4 windows and they all have their own scales now. So the SWR goes from 1 to 10, the return loss goes from 0 to, I don't know what, negative 30 dB. So they all have their own scales now, so you can all see all of those simultaneously. And, you know, you just can't do that with the little thing itself, but the data is all there. So a 2-port measurement, probably won't mess with this very much, but this is a 433 megahertz bandpass filter. Okay, so a bandpass filter is supposed to pass a certain band of frequencies and reject everything else. So the things you really want to know about these usually is what's the insertion loss. When I put this in the signal path, it's going to lose something because it's going through this filter. So you want to know how much you lose, and then you want to know how wide it is. So I put marker 1 sort of in the middle. That said 433. I ended up at 433.7. But as you can see, that's the maximum band. That's the least loss you're going to have, and it's about negative 2.2 dB. So that's telling me the insertion loss. When I put this in the circuit, I'm losing 2.2 dB minimum through this in the pass band. And if you look on some of your tests, I think it says the bandwidth is at the negative 3 dB points. When a filter rolls off 3 dB on either side, that's where you calculate the bandwidth. So you take negative 2.2 and you add 3, I want to be at negative 5.2. So again, we got discrete frequencies. I moved those other 2 markers as close as I could get. And so that's the bandwidth. So it says that delta 3 minus 2, it's about 7.7 megahertz bandwidth with a 2.2 dB insertion loss. And you can see on the low end it falls off pretty quickly. On the high end it doesn't really cut off that much. But it allows you to see all these things. So if you're going to say you had an FM, a preamp for 2 meters up on the tower, and you wanted to cut out the FM stations because they're nearby and they're overloading it, you can make a little filter to notch out that FM frequencies, and you can measure it with this and see how well will it pass the 2 meter frequencies that I want, how well will it reject the FM broadcast band that I don't want. So to get all those pretty pictures, what do you have to do? Okay, so to set this up, you set the sweep frequency range, that 13 to 23 I had. So I kind of violated my thing here because I wanted to see both at the same time. But that should only cover the frequencies of interest to get better resolution. So what does that mean? Well, I could look at my 20-meter dipole, and I could scan from 1 megahertz to 300 megahertz, just because I can. But if you take 300 megahertz and 300 sample points, that's 1 megahertz per sample. So we'll be sampling at 13 megahertz, 14 megahertz, 15 megahertz, all the way up to 300. Well, so almost all of those samples you don't care about because you're just carrying about 20 meters. If you do 14 megahertz to 14.3 megahertz, now you got 300 kilohertz divided by 300 points. That's every kilohertz. So you're going to get a sample at 14 megahertz, 14.001, 14.002. So that's plenty good enough to mess around with antennas. So you really want to make that sweep range the smallest you can get it. And then calibrate the unit. This is what everybody hates, but this should be done on every device which is possible. That doesn't just apply to this. You can calibrate this. You can calibrate that $25,000 one. They all should be calibrated to get an accurate reading of what you're actually seeing. And that's why they all come with these calibration kits. And I say to calibrate at the reference plane. Okay, what does that mean? Well, I can calibrate it right here, and that's better than nothing. But if you want to actually measure what's at your antenna, so say you're going to put up a new antenna, if you have the coax, and it doesn't have to be on the tower, up a tree, or whatever, it can be laying on the floor here. What you want to do is hook the coax here, and these reference loads, which are going to go through the open short load, you want to put those at the end of the coax that's going to hook to the antenna. So what that does is mathematically it disappears the coax. That'll be gone. It'll measure what's at the antenna directly, even though you've got loss in the cable, you've got delay in the cable, you've got everything else. So if you really want to know what's going on with the antenna, you have to calibrate it. None of these things can measure that. Any transmission line is an impedance transformer. And it's kind of weird, but this is a crazy example. If you have just a pure 100 ohm resistor, and you put that right here, and it'll say R equals 100, X equals 0, right? There's no reaction, it's a 100 ohm resistor. If I put a quarter wavelength transmission line between that 100 ohm resistor and here, it'll show it's 25 ohms with no reactance. That'll show as a 25 ohm resistor, even though it's clearly it's 100 ohms, because of the transmission line. The coax completely changes those, and in between there, that 100 ohm resistor will actually look like it's partially reactive, capacitive, or inductive. That's all because of the transmission line effect of that cable. So you can't really get a good measurement without calibrating at the reference plane. Like I said, you can do it here, and that's better, but if it's possible, you want to actually measure that at the transmission line, do those loads. So you want to do the sweep, you want to calibrate it, then you select which traces to display. So you can do up to 1 to 4. You can pick any of them or all of them. And then for each trace, you want to set what's called the format, that he calls it. And that's what you want to look at. Is that the SWR? Is that return loss? Is that a Smith chart? The scale, again, you usually don't have to do that because he picks pretty good scales by default. And the channel. And all the channel is this a 1 or a 2-port measurement? That's all that means. Then you can store that. Once you do all that, you can store it, and you never have to do that again for that particular antenna. Yeah, Jim?
Let's say I'm out of my house, and I'm trying to pull one megahertz. Unhook that coax, hook it up to that machine. What's it going to do?
It'll measure what's at the ballon. I mean, it won't measure really the antenna. It'll measure the antenna through the ballon, but it just measures wherever you've calibrated it. That point is what it'll measure what's there. So if you had like a 200 ohm antenna with a 40 ohm ballon, it should measure 50 ohms, if that's kind of what you're asking.
Well, it's one of those things, if I take that off, put that machine on it, it's going to tell me what kind of loss I've got in the coax.
Well, not directly, no. No, I mean, that's the thing. You really want to know what that loss is. There are ways to measure it. That's another talk. But yes, you can do that. It is possible to measure the loss, but not this way, not by hooking it up through there.
So you have to hook it up to the ballon rather than coax.
This thing?
Yeah.
Why did I? No. Well, you can hook it to the coax, but again, you want to calibrate that coax where it goes with the ballon up there. And then that'll read what the ballon sees, if that makes sense. So if it's a 4 to 1, you should read 50 ohms more or less, up there.
But will it handle? I've got an inverter that Allen, always in it for about what can that machine make?
Well, measure the impedance in the SWR, and typically you just want to know what it is at the balun, because that's what you're feeding. I mean, you know, because the other side of the balun next to the antenna, so.
Maybe you can go really good reference point is the what my transmission line. Well, you might calculate the transmission line separate, but it'll give you a good idea.
Yeah, well, I mean, you could hit it right to the antenna, and it should show like 200 ohms, say, if you're trying to match it with a 4-to-1. I mean, you can hook it to the antenna. But the point is, if you're running a transmission line in between there, that's going to change everything. And that's why you really want to calibrate it at the end of your transmission line. Okay, and all that looks kind of complicated. It takes probably 3 or 4 minutes. So all I'm going to say about this is the NanoVNA. I bought a nice cover for it because I'm a klutz. So you can see port 1 there. It shows the arrow coming out. If that goes back into port 1, that's the well-known S11 measurement. That's a 1-port measurement. If it comes out of port 1 and goes through into port 2, that's an S21. So let's get into menu stuff now, because this is what you have to do to set it up. So if you're sitting there and there's nothing showing on the screen, it's just those traces like we saw. If you touch anywhere on the screen, it'll bring up a menu. It brings up the last menu you used. Okay, well, we're going to start with the main menu, and you'll see on these other menus, there's a back at the bottom of every one. You can say back, back, back until you get to the main menu. So on the main menu, you can set up the display, you can set up the markers, you can set up the stimulus, and you can calibrate it. Recall we're not going to talk about because that just recalls the 7 things you stored. So it just says recall 0 through 6, so there's really nothing to that. The config, you can calibrate the touch screen, you can set the language, you can set the brightness, stuff like that, so we're not going to talk about that either. Storage, if you say storage, it'll just say, do you want to store this as an S1P or S2P file? That's the touchstone files. So we're going to talk about that as top 4, okay? So if I touch display, then I get the display submenu, okay, this display menu. Now it has trace, format, scale, channel, which we're going to talk about. Transform makes this into more of a time domain thing, which you can measure cable length and stuff. Again, we don't have any time to talk about that today. The sweep points, that's that 301. So these are the things I say you set once, you say sweep points 301, you're kind of done. Bandwidth, same thing, 1000 hertz, you're done. So the only thing you'll have to actually change if you're measuring different things typically are those first 4. So I hit trace. So now in the trace menu, you see trace 0 through 3. Okay, the way he has this, if it's a white background, that trace isn't enabled. You won't see that on the screen. So trace 1 and trace 2 are enabled, and trace 1 with the check mark is the active trace. And what that means is when I go through here and I'm going to have to set what I want to look at, the one with the check mark is the one that you're actually doing the operation on. That's the active trace. Okay, and if you hit like the trace that's active, it'll turn it off. If you hit the other one, if I hit trace 2 right now, it'll make that the active trace. It'll flip it from trace 1 to trace 2. So that's pretty straightforward. The colors all match. Trace 1 is blue, trace 2 is whatever color that is, kind of yellowish green. And so you set the trace. So the first thing you'll do, you say display, trace menu, and I want trace 1 or whatever. So then you get that back button at the bottom, and we'll go back to the display menu, and the thing under trace was format. So if you go to format now, it says, do you want that trace to be a log mag, which is return phase, which you probably won't ever do. Delay gets in again to measuring like cable length, which we don't have time to mess with today. Smith is checked, that's why you see a Smith chart. SWR, the magnitude of the impedance. If you say more, you can plot the real part, the imaginary we talked about, some other various things you can do. So we went through, we said, I want trace 1, I want it to be a Smith chart, and then you go back again, and after the trace and the format was the scale menu. Usually, again, you don't have to do anything with this. Okay, he defaults it pretty good. If you want to, you can set the reference value. So what's the reference value? Well, in SWR, it's usually 1, because 1 to 1 is the best case. And then you can put that 1 to 1 SWR anywhere on that reference. All those horizontal lines, he goes from 0 to 11, or 0 to 10. You can move that around. Again, you're not going to have to ever do any of this. And the electrical delay, again, you can actually set this up and it'll tell you what the length of the cable is based on some other things. So again, you really don't have to do much with this, but you can if you want. And then after that, we had to go back again. Whoops. You go back again, not forward. You go back onto the menu, and it's the channel submenu, and you just say, is it a 1 or 2 port measurement? So they're all pretty straightforward. You say, I want trace 1, I want it to be SWR. The scale you probably don't have to mess with, and it's a 1 port measurement. So it's really that quick to set the thing up. So if you back out of this now to the main menu again, and you get to the marker menu, so select marker is just like that trace menu. There's 4 markers. If you touch one, it'll turn that marker on and make it active. You can make multiple ones active like we saw in that bandpass filter. And to select it to make it active, that's the one that you can move. But he's made it pretty easy, like that one that had the 3 markers on it, the bandpass. If you just take it or take a stylus or your finger, if you touch a marker, it'll make that one active. Whether it's if 1 is active and you want to move 3, if you touch 3, it'll automatically make 3 active and you can drag it around. Or you can go here and make it active through the menu, but it's a lot easier just to touch it. Search, that's where you can search for minimum and maximum, like for SWR. Operations, you'll never use. Smith value, we can get into that next time, if there is a next time. That'll allow you to measure directly, like if you have capacitors or inductors and you don't know what they are, it will actually tell you the value of that. It'll say this is an 18.2 picofarad capacitor. Okay, that's all set up as Smith value. So go back to that, the main one, and we have the stimulus menu. Okay, this is also pretty straightforward. You could set the start and stop frequencies. So like this one was from 1 megahertz to 50 megahertz. I prefer that. You can also set the center and the span. And that's used more if you are doing something like a filter. You could say I want the center to be 433 megahertz, and I want the span to be 20 megahertz. So it'll go 10 megahertz either side of the center. I don't usually use that. I use the start and stop. CW frequency, like I said, this thing is always sweeping, but if you want to make this a signal generator, you turn on CW frequency and put in the frequency, and it'll just generate that frequency. Okay, it's just like a signal generator. Analog frequency, we're going to talk next page. And since this is constantly sweeping, if you don't want to change any parameters, you just want it to quit, you click pause sweep, and it'll just stop the sweep until you enable it, and then it'll just start up again. So he's made this pretty easy. So again, if you want to check your 20-meter dipole like he talked about, you need to set up the stimulus. You say stimulus, amateur frequency, and when you hit amateur frequency, you get this screen. So he has ham. He's got 160 meters all the way up to 1.2 gigahertz. So he has already programmed in. So if you want to do your 20-meter dipole, you just do stimulus, amateur frequency, ham 20, and it's set up. Now that says 14 to 14.3, just because he doesn't have space to put it, but it actually goes to 14.35. He knows what the bands are, and they're already programmed in. So you can set the stimulus very quickly. The well-known calibrate menu. Okay, so when you go to the calibrate menu, now there's calibrate power. So the power is that +1 dBm over there. So again, that's something you set once and never mess with it. You can save this, but when you go through the calibration, it also has the save screen, so I'm not exactly sure why that's there. Reset will actually reset all the parameters. So say you've already calibrated this to something, but you want to erase that out because you want to recalibrate it, so you do a reset. The apply, I don't know why you would ever not want to apply it. The only thing I could think of is say you calibrated this for 2 meters, and now you want to check your 20-meter dipole, but you don't want to go through all the calibration. I think you can unapply it, and it just runs kind of raw, open loop, if you will. So that one's usually never unchecked. And then, of course, you can go back. Clear all, just clears out everything. You probably don't want to do that unless you're just ready to, give up and start over again with everything. So how do you actually calibrate this now? Okay, so when you come to this menu, we'll go through it. That's the procedure on the next thing. First, you want to set up that frequency range in the stimulus menu again, because you only want to use the frequencies that you really want to look at. So you set up that in the stimulus menu, then you go to this calibrate menu and hit reset. That'll clear out any previous calibration data. Then that top one that said calibrate, you click calibrate. We'll look at a picture of this. Yeah, sure.
What happens if you don't get the reset?
Good question. I think it tries to calibrate on top of the calibration, and I don't know if that's actually bad, but everything I've read and just I just always reset it because they say you should do that just to make sure you clear out any previous. It will, seems to work, but reset just says, okay, I'm starting from scratch, you know, because I think it'll try to correct. When it reads, it's already reading a corrected value, and then it'll try to correct the corrected value, is my take on what's going on. It's kind of hard to prove because it's confusing. But, yeah, so anyway, you say reset, and then you go up the top, says calibrate. And we'll show you the screen here in a couple of slides. So, what's going to happen with that is it'll come up and it'll have open, short, load, I think what's next, the isolation and through. So it'll just come up and it'll just be kind of sitting there looking at you. And so what you do, you put an open load on port 1. Or for HF, you really don't need an open because an open's an open. VHF might be marginal. UHF, you probably do want to put an open load. That sounds kind of stupid because it's open, but there is a capacitance to deal with that. So if you're working like at UHF, you probably want to do that. Well, you put the open load on here at the reference plane again. So here or at the end of your coax, if you actually have that coax that you're going to hook to antenna, you put the open load at the end of the coax at the reference plane and you select open. So when you select open, it'll say like performing open calibration, please wait. And then when it's done, it'll put a check mark on open and it'll actually highlight short. So you take this off, put a shorted load on there, and you touch short. And it'll say, you know, performing short, please wait. And then it'll check that. Then it'll light up load. So you take that off and you put a 50 ohm load on there, select load, performing, please wait. So when you're done with the load, it'll check that. And so there's two things you can do at this point. If you're doing a one-port measurement, which probably most of the things you do will be, you can just select done. And you can skip the other two. And when you do done, it will say, where do you want to save this configuration, which one of those 7 bins. Okay, if you want to do the full 2-port, at this point isolation is lit up. And if you hit isolation, well, what you're supposed to do before you hit isolation, if you have another 50 ohm load, you put it on port 2. If not, you move it the one on port 1 to port 2, then you select isolation, and it'll do the same gizmo again. Then you take that off and you hook a jumper between port 1 and port 2, and you hit through. And what that's doing, it's setting the 0 dB reference level. Okay, the way it knew that that filter had a 2.2 dB loss is it compares it to what a piece of wire is. So the piece of wire is 0 dB, it should have no loss. And likewise, if you test like a preamp, it knows where 0 is, so it can tell you if there's gain or loss. And then you select done, and it goes to the save menu as before. So this is what it looks like. You can see on here, open, short, all those are checked. And when you go through all that, and you hit done, then this is what comes up, the save menu. So you can see that C4 we had before on the dipole. You can see it says 13 to 23 megahertz. So that the dipole was saved in there and various other things I was goofing around with. So that's really about it. If there's any questions, actually, if you want to sit down, if you're not absolutely totally sick of this by now, and if you're still awake, we can actually run through. I brought a little fake 5 megahertz dipole with me. So we can actually go through there and hook this up. We can run through setting the frequency range, doing the calibration, and actually taking an SWR plot of that. And you'll see that whole thing takes a few minutes. I mean, it's really quick to do. So that's all I really have on here. Like I said, I hope it's not overwhelming. I think it's one of those things you have to play with. And once you play with it a few times, you'll see there's really not that much stuff you have to do with this. You know, once you set the range, calibrate it, tell it what you want to look at, and then you're done. So, yeah. That's just one of the versions. I don't know what the F is for. There's also a -H, and there's a -H4. Yeah, is that an H? Yeah, I think the H4 is just a 4-inch screen, pretty much of that, I believe, right? It's a bigger screen. It's this screen size, but it's an H. Yeah. So go ahead, sorry. Yeah, so the H were kind of two brand. Again, this was open source. So some people said, oh, I'd like to do it this way. Some would like to do it that way. So there's various models of doing. Yeah, they were the first one, I think, right? And then they started going to the bigger screens and things. And those don't even have a case, I believe, right? So then they got a little more sophisticated, got bigger and all that stuff. But they're all effectively the same.
ago that have never used it. Said some were better than others. How do you tell the one you got is doing?
Good question. I mean,
Other than the variant is allowed.
yeah, I mean, that's kind of what you'd have to do, right? Or compare it with another one of these and just see what you get. I have tried that between these two just to see, and if I calibrate, I've got a 2-meter J-pole I was playing with, and I got 50 feet of LMR 240. So if I calibrate both of these, they're like almost dead on the SWR and the frequency. Now, I can't understand this because usually if you measure at the antenna, the SWR is worse than at the end of the coax, because the loss in the coax makes the SWR seem better even though it's not. But when I did it with this, it said it was a 5-to-1 SWR, and it's really like a 1.01 SWR. I don't either something was wrong or I'm not understanding it. But if you don't calibrate these, they give you wildly different answers. Okay, but if you calibrate them, these things are almost exactly the same. So, but yeah, I don't think there's any real good tell. One thing they do a lot, if you want it, one way to tell is on the Smith chart thing again. If you do the open short load and you have a Smith chart up, an open should be clear at the very, well, I don't have it up here, the very right side of the Smith chart on that circle is an open. The very left side on the circle, on that horizontal line, the only straight line on the whole chart, is a short, and 50 ohms is dead center. So if you calibrate that, and then have the Smith chart up and you have it open, that dot should be clear on the right side. If you screw on the short, it should be clear on the left side, and if you put the 50 ohm load, it should be dead center in the middle. If it doesn't do that, then it's not calibrating correctly, because that's what you're calibrating for. You're telling it, this is 50 ohms, so it should say, okay, that needs to be right in the middle. And if they don't calibrate right, that's the easiest way to kind of tell if the calibration worked.
Is it useful for dealing with 70 ohm CATV hardline?
Yeah, I mean, I use it for that. I mean, it has an SWR at 1.2 or something because it's 70 ohms, but pretty much the other stuff is, I mean, you can still measure. Right. Yeah, because I got a bunch of old RG59 that I had for some other project I was working on a long time ago, like a 1,000-foot roll. So I try to use it for stuff because it's, got a lot of it. But it will work for those, but it won't read exactly the values. And again, it's just math. You can correct for that. In fact, this guy does have built-in. You can tell that it's a 75 ohm system, and basically it just does the math to correct for the 75 ohms. I'll show you later, because I know life is math. What is that? What you say? Life is math. Everything else is just details. I think that's what President Biden said. Yeah, I was going to put in a thing of equations, but I didn't. You know them all already anyway, so it doesn't matter. Yeah, well, Fourier on these is what they use. But anyway, like I said, if you want to go through this, I did bring some stuff. We could take 10 minutes and actually see going through the process. Maybe it would stick better than me just talking, but we can go through that and do it. Sir David wants to do that, so we can do that. Anything else? I mean, that's, I know it kind of ran through quick, but okay, well. I always feel good if I don't